let us study the chapter known as Carbohydrates Chemistry. Carbohydrates are the most abundant organic molecules which are present in the nature. These carbohydrates are primarily composed of the elements carbon, hydrogen, and oxygen. According to the definition, the carbohydrates may be defined as polyhydroxyaldehydes or ketones or compounds which produce them on hydrolysis. So what is the meaning of polyhydroxyaldehydes or ketones? Actually, these carbohydrates are of two families. One is an aldehyde family, where aldehyde is a functional group, and another one is a ketone family, where ketone is a functional group, which are incorporated with carbon atoms, hydrogen, and hydroxyl molecules. Because of this, these carbohydrates are generally referred as polyhydroxyaldehydes or polyhydroxyketones, which are generally produce them on hydrolysis. Now let us study what are the functions of carbohydrates. These carbohydrates participate in wide range of functions. That is, they are the most abundant dietary source of energy, which can give like 4 calories per gram for all organisms. And another important thing, that these carbohydrates are very important for the synthesis of other organic molecules like fats and amino acids. That is, the biosynthesis of fatty acids and amino acids, which are generally depends on carbohydrates. Next is the carbohydrates forms an important component in structure of cell membrane, and not only that, they also involve in the cellular functions such as like growth, adhesion, and fertilization. These carbohydrates are generally known as glycoproteins or glycolipids, which means a carbohydrate which is incorporated with a protein known as a glycoprotein, and if carbohydrate is incorporated with a lipid known as glycolipid. Now, this carbohydrates also forms a structural component of many organisms, which includes the fiber of plants, that is in the form of cellulose, exoskeleton of some insects, you can see in the cockroach, and also the cell wall of certain microorganisms, which are generally made up of carbohydrates, mostly polysaccharides. The final thing is the carbohydrates also serves as the storage form of energy, that is in the form of glycogen. It is very important as it stores the energy for the immediate requirements as the body demands. Now, let us study the classification of carbohydrates. These carbohydrates are generally called as saccharides, which is because in Greek terminology, saccharon, which means sugar. These carbohydrates are broadly classified into 3 major groups, that is monosaccharides, oligosaccharides, and polysaccharides. This categorization of different saccharides are based on the number of sugar units which are present in that particular carbohydrate molecule. That is, mono means if a sugar unit is only 1. Oligo means which are generally called as like 2 to 10 sugar units which are held together, and polysaccharides which is more than 10 sugar units which is present in a particular carbohydrate molecule. It is very interesting to know that the mono and oligosaccharides are sweet to taste, and these polysaccharides are tasteless. Now, let us study in detail about monosaccharides. I already mentioned in the beginning, that is when we studied the definition of carbohydrates. Let's review again. What is the definition of carbohydrate here? The carbohydrates are polyhydroxyaldehydes or ketones or compounds which produce them on hydrolysis. And we also studied the carbohydrates has two families. One is the aldehyde family, another one is the ketone family. So same like that, these monosaccharides exist in two different forms, that is aldehyde form and ketone form. And the monosaccharides are the sugars with aldehyde group known as aldoses, and with ketone group is generally referred as ketoses. The aldehyde you can see here, the aldehyde has the functional group CHO, and the ketone which is generally has C double bond O. So these are the two functional groups which we generally seen in carbohydrates. So now let us study about oligosaccharides. These oligosaccharides contains 2 to 10 monosaccharides molecules which are liberated on hydrolysis. That is based on the number monosaccharide units present, the oligosaccharides are further classified or further divided into disaccharides, trisaccharides, etc. That is, if you take disaccharide, the disaccharide consists of two monosaccharide units held together by means of a glycosidic bond. And trisaccharides, same, the three monosaccharide units which are held together by glycosidic bond. So whatever it is, if the number of sugar units are between 2 to 10, then they are generally referred as oligosaccharides. Next, study about polysaccharides. Polysaccharides are generally known as the polymers of monosaccharides. That is, a number of monosaccharide units which are held together by a glycosidic bond. And all the polysaccharides which are generally of very high molecular weight. I already mentioned you that these particular polysaccharides are usually tasteless, and these polysaccharides also form colloids by combining with water. And it is very important to know that these polysaccharides are also divided into two types. One is known as the homopolysaccharide, where this particular polysaccharide contain identical unit of monosaccharide units. And the heteropolysaccharide contains different types of monosaccharide units which are held together by means of glycosidic bond. Now, let us study the structural aspects of monosaccharides. Now in this particular monosaccharides, it is very important to know the isomerism. That is, the stereoisomerism is an important character of monosaccharides, where the stereoisomers are the compounds that have the same structural formula but differ in their spatial configuration. Example, I already told you that this particular carbohydrate exists in two different forms. That is, aldehydes, the sugar with aldehydes known as aldoses, and ketones, the sugar with ketone is known as ketoses. A particular monosaccharide, if we take an example, that is glucose, which has formula C6H12O6. The formula is same in glucose and even in fructose. But this particular glucose is known as hexose with aldehyde as the functional group. That's why it is known as aldohexose. And fructose, if you see, it has a ketone. That's why it is known as a ketohexose. So what is the difference between the glucose and fructose here? The glucose is aldohexose and fructose is a ketohexose. That is very important point to note. That's why it is very important to know about stereoisomerism. Now I think all of you understand well that these stereoisomers are the structural compounds that have the same structural formula but they differ in their spatial configuration. And it is very important to know also some basic chemistry that all of you studied in your intermediate classes, that the carbon has a valency 4. And a carbon is said to be asymmetric when it is attached to 4 different atoms or groups. That determines the possible isomers of a given compound, which is equal to 2n. Glucose, which contains 4 asymmetric carbons, and which glucose contains totally 16 isomers. It is just a basic chemistry, and whatever you need to know in this particular slide is carbon has a valency 4 and glucose has totally 16 isomers, and you should have a basic idea about stereoisomerism. So what is a stereoisomerism and what is the difference between glucose and fructose, and mainly to differentiate between aldoses and ketoses, it is very important for not to confuse. Okay, let us move on to the structural aspects of carbohydrates, and we'll come to the formula again. We already studied the carbohydrates are generally known as hydrates of carbon. In the name of carbohydrates itself, you can see carbo, which means carbon, hydrates means water. So CH2O is a basic component which is generally seen in a carbohydrate structure, and depending upon the number of carbon atoms, the formula can be written as CnH2ON. N means number of carbon atoms. And it is very important here to know that the minimum number of carbon atoms which are present in carbohydrates is 3. So according to our formula CnH2ON, when n is equal to 3, the formula is C3H6O3. So this C3H6O3, which has 3 carbon atoms, generally known as triose, means a saccharide with 3 carbons. That's why it is known as triose. This triose also exists in two forms. One is aldehyde form, another one is ketone form. The aldehyde form, it is known as aldotriose, and ketone form, it is known as ketotriose. And here I want to mention another important point to all of you, that if you identify a functional group, that is, you can see in aldehydes, always the aldehyde group which can be seen at carbon 1, and ketone group is always seen at C2, that is carbon 2. Now let us study what is glyceraldehyde. The glyceraldehyde is generally known as the reference carbohydrate. Why? Because the glyceraldehyde, the name itself you can see in aldehyde, which means it is an aldose with 3 carbon units, so it is known as aldotriose. So what is the aldotriose? Which has a same molecular formula, that is C3H6O3, which is known as glyceraldehyde. So that's why this glyceraldehyde is the simplest monosaccharide, and it is very important point to know. Now let us see the structure of glyceraldehyde. The glyceraldehyde, I already told you, it is a triose, and it is a simplest monosaccharide with one asymmetric carbon atom. You can see here the glyceraldehyde is a triose with 3 carbon atoms, carbon 1, carbon 2 and carbon 3. So in this glyceraldehyde, you can see the functional group aldehyde, which is seen at carbon 1. So this particular glyceraldehyde exists as 2 stereoisomers, and which has been chosen as the reference carbohydrate to represent the structure of all other carbohydrates. Now let us see what is epimers. Two monosaccharides differs from each other, that is in their configuration, around a single specific carbon atom. Then these two compounds are known as epimers to each other, which means, for example, if you take 2 monosaccharides, if 2 monosaccharides differ from each other around a specific carbon, that is orientation of H and OH is different in only one carbon, then those 2 monosaccharides are referred as epimers to each other. Here you can see an example where you can see the structure like glucose and mannose. So in glucose, you can see in second carbon, the OH is oriented towards right side. The same thing in mannose. In second carbon, the OH is oriented towards left side. And if you see all other carbons from C1 to C6, everything is same, which is of mannose. But the only difference between glucose and mannose you can see at carbon 2. At carbon 2 of glucose, OH is oriented towards right side, and carbon 2 of mannose is oriented towards left side. According to our definition, if 2 monosaccharides differs from each other around single specific carbon atom. What is the single specific carbon atom over here? C2. The carbon 2 is a single specific carbon atom which differs between glucose and mannose. That's why these two compounds are known as epimers to each other. In the same way, you can also see another example between the glucose and galactose. The difference between glucose and galactose you can see at C4. The orientation of H and OH in C4 is different, and elsewhere everything is same between glucose and galactose. So that's why these glucose and galactose are also known as epimers to each other with regard to the carbon 4. So that's why the glucose and mannose are known as C2 epimers and the glucose and galactose known as C4 epimers. So the process of the interconversion of glucose to mannose and mannose to glucose, or maybe from glucose to galactose and galactose to glucose, is known as epimerization, and there are the enzymes which mediate this process. They are called as epimerases. Epimerases are the enzymes which are responsible for this epimerization. So what is the enzyme which is responsible for the conversion of glucose to mannose and mannose to glucose? It is C2 epimerase, which is very important point to note. C2 epimerase is an enzyme which is responsible for the interconversion of glucose to mannose and mannose to glucose. In the same way, the enzyme which is responsible for the conversion of glucose to galactose and galactose to glucose is generally referred as C4 epimerase. It is very important point to note. So we'll move on to another small topic which is known as enantiomers. Here, enantiomers are a special type of stereoisomers. And simply we can say the enantiomers are the compounds which are like mirror images of each other. And the majority of the sugars in higher animals, including man, which are generally present as D type. So like that, the enantiomer of D is nothing but L, and enantiomer of L is generally referred as D because both are stereoisomers and which are mirror images of each other. And clinically it is not important, just you should know like what is a mirror image and what is the difference between the D and L isomers. Simply the D and L isomers, which can be represented according to the optical activity of the sugars, that is depending upon the optical orientation between H and OH with respect to the carbon. The D means dextrorotatory and L means levorotatory. That's all you need to know. So in our common medical practice, D-glucose, you can say this D-glucose is known as dextrose. Why? Because our body can metabolize mostly D types of sugars and not the L type, which is the important point to remember. Now finally, we will find out what is the structure of glucose. Initially in the beginning of the chapter, I just gave you a small introduction about the glucose and fructose. So what is the glucose over here? The glucose is iohexose. The glucose is a 6 carbon atom and it is a monosaccharide. And this particular glucose, which can be written even in cyclic forms. So, for the better understanding of glucose structure, first we need to know the formation of hemiacetal and hemiketal. That is, if a glucose is undergoing hemiacetal, or if it is converting into hemiacetal, then it is known as an hemiacetal glucose. So how these particular hemiacetals and hemiketals are formed? That is, how the hemiacetal glucose is formed. The hemiacetal glucose is formed when an aldehyde group reacts with the alcohol group. So that is, the aldehyde group of a monosaccharide, for example, you can take that monosaccharide as a glucose. So you already know the glucose has so many hydroxyl groups. So according to the definition of carbohydrates itself, we already said that the carbohydrates are polyhydroxyaldehydes or ketones. So you already know the functional group of aldehyde is present at C1 and in ketone which is present at C2. So that particular functional group, it may be aldehyde or ketone which reacts with the OH group of same alcohol. That is OH group of same monosaccharide, not alcohol. So the hydroxyl group of a monosaccharide which reacts with its own aldehyde or own keto functional group, then the resultant compound which is formed is known as hemiacetal or hemiketal. Example, if it is glucose, it is known as hemiacetal glucose. Glucose doesn't form hemiketal. Why? Because glucose doesn't contain a ketone group, which is very important to know. Fructose can form hemiketal and glucose can form hemiacetal because of the presence of aldehyde and ketone group between glucose and fructose. So here, how the aldehyde group reacts with the alcohol. If you see the glucose structure, the OH group of carbon 5 is held towards right side, which reacts with the carbon 1, that is aldehyde group. It is very important to know. So where you can see here, in this particular structure, the glucose, the C5, the OH group which is present at the C5 reacts with aldehyde group. Then the OH leaves this particular place and will occupy the place over here. So whatever the O which is present here is removed and it will be hanging in the middle. So here it also forms H and OH because the OH which is present at C5 is accommodated in the place of O, which causes the loss of double bond and it forms single bond, and whatever the O which is like removed, which can be hanging in the middle. So this particular structure, whatever is formed, is known as hemiacetal glucose. It is very important to know. So according to the H and OH groups which are present at the C1 of hemiacetyl glucose, the D-glucose can be named as alpha or beta. If OH group of a D-glucose is oriented toward right side, then it is known as alpha, which is known as alpha D-glucose. If the same OH group of C1 is oriented towards left side, then it is known as beta, that is beta D-glucose. So now what is the difference between alpha D-glucose and beta D-glucose? Only at C1. In alpha D-glucose, the OH group at C1 is at right hand side, and in beta D-glucose, the OH group at C1 is at left hand side. So what is this orientation literally means? It's nothing but an optical activity of the sugars. For example, a freshly prepared glucose solution is in the form of alpha D-glucose, so which possess an optical activity of 112.2 degrees, and slowly it can convert into equilibrium glucose. What is the equilibrium glucose? It is normal glucose without hemiacetal or hemiketal formation. You already saw the normal structure of glucose. Means whenever a glucose solution is made that is in the form of alpha D-glucose, so its optical activity is 112.2 degrees. After some time, the optical activity gradually decreases from 112.2 degrees to 52.7, where it forms an equilibrium glucose, and it is not hemiacetal glucose. And this particular equilibrium glucose is added with strong alkali like sodium hydroxide. From 52.7 degrees, the optical activity of the normal equilibrium glucose further decrease to 18.7. Then the OH group, which is held at carbon 1, shift towards left because of decrease in its optical activity from 52.7 to 18.7. Then it is referred as beta D-glucose. And the interconversion of alpha D-glucose to beta D-glucose with respect to the equilibrium glucose is known as mutarotation. Mutarotation is a process of interconversion of alpha D-glucose to beta D-glucose or beta D-glucose to alpha D-glucose with respect to that of equilibrium glucose, which is known as mutarotation. And now if you see the difference between the alpha D-glucose and beta D-glucose is only at C1. If you see all other C2, C3, C4, C5 and C6 all are same. In alpha D-glucose, the OH is oriented towards right side, and in beta D-glucose, the OH is oriented towards left side. So, this alpha D-glucose and beta D-glucose are known as anomers to each other. They are known as anomers. So now what is the definition of anomers? If two monosaccharides differs from each other around its configuration at C1, known as anomers to each other. So here if you see the alpha D-glucose and beta D-glucose, they differ from each other at C1. And the process of interconversion is known as mutarotation, and the two carbons, that is C1, which are undergoing optical activity, which is alpha D-glucose and beta D-glucose, are known as epimers to each other. Now, here we will see in this particular slide the structures, the important structures which we are going through in our next topics or in like metabolisms. These are the things which are like important to know. You already studied the triose. The triose is aldotriose. In aldotriose you also already studied the structure of glyceraldehyde. What is the molecular formula for the glyceraldehyde? Which is C3H6O3. And what is known as aldotriose. So what is the ketotriose? Which also has the same formula, C3H6 and O3. And I already told you the aldehyde is always present at C1 and ketone is always present at C2. So this particular structure is known as dihydroxyacetone. So what is the dihydroxyacetone? The dihydroxyacetone is known as ketotriose. Glyceraldehyde is known as aldotriose. Like that, you have some of the structures which are in ketone form. For example, xylulose. Even in xylulose you can see second carbon, you can see ketone group. But it is very important to remember the third carbon, the OH is held towards left in xylulose. It is very important to remember because this particular xylulose may come in HMP pathway and uronic acid pathway, where you have to identify the structure. It's very important to know. So here at carbon 1 you have H and OH, which is generally written as CH2OH. And second carbon you have a functional group, that is C double bond O. And at third carbon OH is oriented towards left and H is right. And in fourth carbon H and OH. And in fifth carbon again CH2OH. This is known as xylulose, which is D. Because of last but one carbon, you have to always see to find out whether it is D or L. So last but one carbon, if OH is on right side, just simply you should know that it is a D configuration. So like that you have like ribulose. So now what is the difference between xylulose and ribulose over here? Here in third carbon the OH is on right side. So all OH you can see in the ribulose is on right side. So it is very easy to differentiate between the xylulose and ribulose, where in xylulose at carbon 3 OH is held towards left, and in ribulose the OH is held towards right at third carbon, and all OH which are of right side. It is very easy to remember. So finally we will see another important structure known as fructose. Fructose, we know it is known as a ketohexose. What is aldohexose? Aldohexose is glucose with same molecular formula of C6H12O6. In fructose you can see here same at carbon 1 H and OH, which can be written as like CH2OH. And according to our rule, always ketone is present at carbon 2 in carbohydrates. So in like second carbon you can see the ketone group. Here also you should know in fructose the HO and H, not HOH. So at third carbon it is reversed. So even in glucose, if you clearly identify, there also the C3 is reversed. Here also the C3 is reversed. Everything will be H and OH. So even in glucose, at carbon 3 itself, OH is directed towards left hand side, and even in fructose. So like this, you have to remember the structures you should be in the position to identify them whenever these particular structures are given. Why? Because sometimes in the MCQ they may give the two structures and they'll ask you what is the enzyme in the middle. So first of all, you should be in the position to identify what are those two structures are, what are the products, and what are the substrates which are converting into products. So you have to identify the substrate and products, then only you can identify what is the enzyme. So this kind of MCQs may also be seen in the exam. That's why at least at these structures you should have some knowledge to know. Okay. Anyway, next is like pseudoheptulose. The pseudoheptulose with 7 carbons. So this is also very easy to remember. Like with 7 carbons with same rule. Ketone at second carbon and at third carbon H and OH is oriented reverse. That is HO is off left side and H on right side. So these are the only ketones which can be widely used. That is dihydroxyacetone, ketotriose, xylulose, ribulose, fructose and pseudoheptulose. These are the structures which are important. So finally, we will study about the pyranose and furanose structures. There is a Havoc projection formulae are depicted by a 6-membered ring which is known as pyran or pyranose ring, or 5-membered ring furan, it is known as the furanose ring. So pyranose is a 6-membered ring and furanose is a 5-membered ring. This particular cyclic form of glucose or fructose can be written on the basis of hemiacetal and hemiketal monosaccharides. You already studied what is a hemiacetal and how hemiacetal glucose is formed. Again, let's review how hemiacetal glucose is formed. When aldehyde group of a monosaccharide reacts with its own alcohol group, that is OH group, then the resultant compound is known as hemiacetal. I already showed you example also. The OH of glucose at carbon 5 is reacted with O at carbon 1 where the double bond is lost, and it also forms single bond and HOH where whatever the OH is raised from the carbon 1 which will be hanging in the middle. So based on this particular hemiacetal and hemiketal formulae, these cyclic form of glucose or fructose can be written. And now let us see. I already briefly told you what is the anomers and what is the meaning of the mutarotation when we studied the hemiacetal and hemiketal itself. Like let's review again. The alpha and beta cyclic forms of D-glucose are known as anomers. What is the meaning of this? I already told you. The alpha D-glucose and beta D-glucose both are anomers to each other. Why they both are anomers to each other? Because they differ from each other in the configuration at carbon 1. Because that carbon 1 is known as anomeric carbon. Always you have to remember, the carbon 1 of any monosaccharide is known as anomeric carbon. So, the alpha D-glucose and beta D-glucose differ at carbon 1, that is at anomeric carbon. That's why they are known as anomers to each other. You already know that in case of alpha anomer, the OH group held by anomeric carbon is on the opposite side of the group, that is CHOH of a sugar ring. This is exactly reverse whatever you can see in the beta anomer. And this, even though the molecular formula is same, these alpha and beta forms, cyclic forms of glucose, are these alpha and beta anomers shows difference in a certain physical and chemical properties. So finally, what is the meaning of a mutarotation now? I already told you, the interconversion of alpha to beta and beta to alpha, that is alpha D glucose is converted to beta D glucose with respect to the equilibrium, and beta D glucose is also converted to alpha D glucose with respect to the equilibrium. This interconversion from alpha to beta, beta to alpha is referred as mutarotation. So how the optical activity changes? I already told you, the freshly prepared glucose solution has 112.2 degrees and it gradually attains an equilibrium, that is 52.7, and when it is presented with strong alkali like sodium hydroxide, the optical activity further decreases to 18.7, and it is very important. Now here you can see how they are like interconverting each other. So here you can see this is known as like D-glucose. The OH at carbon 5 is reacted with the O which is present at carbon 1, and there is a loss of double bond because of OH is coming and sitting over here. What is happening? A single bond is created and it will become HOH, and that O will be hanging in the middle. And this is the pyranose ring. 1, 2, 3, 4, 5, 6. 6-sided pyranose ring. The numbering can be made from here, where whatever the O which is released from the carbon 1, which is hanging in the middle, can be written here. So from here the numbering is done like 1, 2, 3, 4, 5, 6 carbons. So what is seen at carbon 1 over here? HOH, because this OH is sitting over here and O will be hanging in the middle, that we already written over here. So here in the carbon 1 you can see HOH. So in carbon 1 what we write? HOH. So what is at carbon 2? Same, HOH. So that's what we wrote, HOH. But we know in the carbon 3 of glucose and galactose and xylulose is different, which is reverse. So in carbon 3 we will write HOH. Here you can see in carbon 3 HOH, and elsewhere HOH. And because of at carbon 5 the OH is sitting at carbon 1, in the carbon 5 you can only see H. That's what you are writing over here. At carbon 5 you have only H, and finally carbon 6 you are having CH2OH. So whatever it is, how you identify whether it is alpha or beta? By seeing carbon 1, right? Because carbon 1 is known as the anomeric carbon. So here you can see the carbon 1 OH is on right hand side, HOH. That's why it is known as alpha, which is known as an equilibrium, which is normal structure with double bond OCHO in the first one. And here you can see the HO is shifted over here in beta. You can see here. So the change can be seen in anomeric carbon. So the interconversion of alpha D glucose to beta D glucose, because it is a pyranose ring, we can also say that alpha D glucopyranose to beta D glucopyranose and vice versa is generally known as mutarotation. And those alpha and beta cyclic forms of D glucose are referred as anomers to each other.